Hello Bobcats. So in this video today we're going to talk about formal charges. Now formal charges is a system used to determine the most stable structure when more than one structure can exist for a compound. When more than one structure can exist for a compound. Okay, so let's take a look at this. Let's look at OCN minus. So it's a polyatomic ion, and if we count our electrons, again we're going to go through the whole process here. So we have 1 times 6 electrons for the oxygen, plus 1 times 4 electrons for the carbon, plus 1 times 5 electrons for the nitrogen, plus there's a negative charge here, which means we have 1 extra electron. So that's 1 plus 5 is 6, 10, 16 electrons. Okay, so now carbon is the least electronegative, so it will go towards the center. And so we have an carbon, a nitrogen, and an oxygen. We've used 4 of the 16. So I start putting electrons around the element, the compound, specifically starting with most electronegative. And so we're going to have 2, so I had 2, 4, 6, 8, 10, 12, 14, 16 electrons. So I've used the 16. I know this nitrogen has 8 valence, and this one has 8, but my carbon only has 4 electrons, so it needs 4 more. So I'm going to take from the rich. Now I'm going to go ahead and take from nitrogen first because it's the least electronegative. So the next possible structure is oxygen, carbon, nitrogen, and so I have a double bond here. I'll have 1, 2, 3, 4, and 2, 4, 6. So I still have 2, 4, 6, 8, 10, 12, 14, 16. My carbon is still not complete yet. It only has 6. So we're going to take from the rich. Now this time oxygen has more lone pairs than nitrogen, so I'm going to take from the oxygen. So we'll end up with O, double bond, C, double bond, N, 1, 2, 3, 4, 1, 2, 3, 4. Now let's look. 2, 4, 6, 8, 10, 12, 14, 16. Then 2, 4, 6, 8, 2, 4, 6, 8 for the carbon, and 2, 4, 6, 8 for the nitrogen. Now this is what you'd think it would be, but there are some other possible structures, and so let's look at this. So look at some of the other possible structures. So I can have, well, let's write this one down first. This is a good one. Double bond carbon, double bond nitrogen. But we can also have this one. This is a possible structure. By the way, I forgot to put my bracket. Remember, anytime there's a charge, we need to put the bracket and the charge. Okay, so now another possible structure for this would be oxygen, triple bond carbon, single bond nitrogen, with a lone pair there and then lone pairs there. Now let's make sure that it is a valid structure. 2, 4, 6, 8, 10, 12, 14, 16 electrons. Those are the 16 from here. Then we have 2, 4, 6, 8 for the oxygen, 2, 4, 6, 8 for the carbon, and 2, 4, 6, 8 for the nitrogen. So it is valid. We also have another valid structure, which would be oxygen, single bond carbon, triple bond nitrogen. And let's see if it's valid. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So all the octets are filled. I got 2, 4, 6, 8, 10, 12, 14, 16 electrons. So it is valid. So how do we know which one is the most stable? Well, what we use is formal charges, just like I said up here. Formal charges are used to determine the most stable structure. And you can have more than one possible. So how do we figure out formal charge? Now I'm going to leave a little bit of space here because I'm actually going to calculate the formal charges below this, but let's write out the rules for formal charge, or how do we determine formal charge. So formal charge is equal to the number of valence electrons minus number of formal electrons. Now, so we know what valence electrons are, but we don't know what formal electrons are. So we need to write down what a formal electron is. So in this case, formal electrons, lone pairs, if we have a lone pair, accounts for 2 formal electrons. A lone pair accounts for 2 formal electrons. Now, I'm not putting the word formal because that's what we're looking for here, is formal. And then a bond accounts for 1 formal electron. Okay, so formal charge comes from looking at valence and formal electrons. So let's go back up here, and if I look at this, we now are going to figure out our formal electrons. So we have oxygen, we have carbon, and we have nitrogen. Now oxygen is going to have remember 1, 2, that's a lone pair, 3, 4, and then each bond excuse me, only counts as 1. So that's 1, 2, 3, 4, 5, 6 formal electrons. So there's 6 valence electrons minus 6 formal electrons, so it has a formal charge of 0. Now carbon in this case has got 4 valence electrons, remember it's valence first and then formal, minus 1, 2, 3, 4. Remember, each bond only accounts for 1 electron, so that's minus 4. So that comes out to be 0. So we have a 0 formal charge here, a 0 formal charge here. And then we have nitrogen, and nitrogen has 5 valence electrons minus 1, 2, 3, 4, 5, 6. 6 formal, so that's a negative 1. So this has a 1 minus formal charge. So we have 0, 0, 1 minus. Over here, oxygen is equal to 6 valence minus 1, 2, 3, 4, 5. So that's 5 valence, 5 formal electrons. So that's a 1 minus. So we have a 1 minus here. Then we have carbon, 4 valence minus 1, 2, 3, 4, 4. So that's going to equal 0. So this has a 0 formal charge. Okay, and then nitrogen is equal to, we have 5 valence electrons minus 1, 2, 3, 4, 5, 6, 7. 7, so that's going to be, or this is a positive up here, sorry, positive, because 6 minus 5 is 1 plus. Sorry about that. And this is going to be a 2 minus. So we have a 2 minus. The reason I can check, and the reason I caught that, is because this 2 minus and 1 plus has to come out to be 1 minus. So this 1 minus matches this 1 minus over here. Then we do the formal charge for this last one. So the oxygen is equal to 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. So that's a negative 1, or 1 minus. Then we have carbon, which has 4 valence electrons minus 1, 2, 3, 4. So that's 0. And then we have nitrogen with 5 valence electrons minus 1, 2, 3, 4, 5. 5. So that's equal to 0. Okay, so the deal is the structure with the least amount of differences in formal charge is the most stable. So let's write that down. The structure with least amount of differences in formal charge is the most stable. Okay, so let's look up here, and this is just a negative 1, 0, 0, negative 1. This one has a bigger difference or more charge here, a 1 plus and a 2 minus. So we know this is not stable. And then we have this one where then we have a negative 1, 0, 0. Okay, so this has the same charge difference that this does. So now we have to decide between this one and this one. So if you have the same charge difference, if there is same charge difference, the negative charge on the most electronegative element will be the most stable. The negative charge on the most electronegative element will be the most stable. So let's look back up here, and this has a negative on oxygen and this has a negative 1 on nitrogen. Oxygen is more electronegative than nitrogen, therefore this is the most stable structure for OCN minus. That's a check to say yes, that's the most stable. I'll put an underline under it just so you know, most stable. Okay, so let's just look at one more and see how that works. So let's practice one more compound and then we will stop this video for today. And this compound, I'm not going to go through all the steps, I'm just going to go through the formal charge step. So this one we have is POCl3 minus. So let me write that structure or that compound down. We have POCl3, not minus, but so, and when I counted this has 32 electrons to use, Okay, and phosphorus is the least electronegative, so I can have this structure where I have P, O, Cl, 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 and then 1, 2, 3, 4, 5, 6. Let me do this again. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. And then everything has an octet. So this is a valid structure. But we also have this structure. In which let's count our electrons. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Now your first question probably is, wait a minute, Mr. Willoughby, we got a problem here. This has an octet around phosphorus, but this actually has 10. Remember, phosphorus is one of those elements that has, as an exception, it can have 8 or 10 electrons. And in the next video, we will talk about what's called the expanded octets, or those exceptions. And so, but first, let's go ahead and discuss this one as formal charge goes. We do know that it's okay to have 10 around phosphorus, and I'll explain in the next video why that's okay. But if I look at formal charges, we have a phosphorus here. It has its 5 valence electrons minus 1, 2, 3, 4, so that equals a 1 plus. Then we have oxygen, or chlorine. Let's do chlorine first. Chlorine is 7 valence electrons minus 1, 2, 3, 4, 5, 6, 7. So that's 7 minus 7, that's 0. And then my oxygen will have 6 valence electrons minus, up here, 1, 2, 3, 4, 5, 6, and then the bond is 1, so that's 7. So this is a 1 minus. So we have 0, 0, 0, 1 plus, 1 minus. Okay, so we have a charge difference here. Now over here, let's go through phosphorus. Again, phosphorus has 5 valence electrons minus 1, 2, 3, 4, 5 formal electrons. So that's 5 minus 5. That comes out to be 0. Chlorine, again, is, they didn't change at all. So we'll say 7 minus 7, that equals 0. And then my oxygen, in this case, 6 valence electrons for oxygen minus 1, 2, 3, 4, 5, 6. Minus 6. So that equals 0. So we have 0, 0, 0, 0, 0. So there is no formal charges on this, so this has the least difference in formal charge. So this structure is the more stable of the two. That's the more stable structure. And that's why we use formal charges. Our next video is going to talk about this expanded octet. And so that's the video for formal charges today, and I will see you later.